I'm doing it. Just gonna happen.
Jump in.
So that was a lot last time. Sort of went impromptu. Any questions? Anything I can help you with? Okay. How's class going? It's always a lot to Bayes, and so we never get to what I want. But one thing we're going to start with today is how did that algorithm work? Because a lot of Bayes is sort of, oh yeah, we're just going to push it to the black box and let it do its thing. But there's sort of an art to understanding what the black box is doing, particularly when you're working with more complicated models. And psychometrics is a big deal. There's a function in R that comes from I think the R to JAGs. Actually, this is RJAGs package, where you can list the samplers, which means what algorithms is JAGs using? JAGs will go and try to choose the most efficient algorithm. It's not super awesome at that, depending on how you phrase your model syntax. There are ways that you can shortcut it to make it go faster. And so when I listed the samplers for the model, this is the very beginning model with the conjugate prior for sigma squared and the conjugate prior for beta. When you load the GLM module, which is loaded by default in R2 JAGs, what I had in my previous syntax, it tells us GLM generic for each of these. What this is sort of trying to say is effectively all these get sampled as a group. So in a step in an iteration, all these are showing up as a group together. And the generic really means, we phrase this where JAGs can tell it's a linear model, just a typical standard linear model, and we can go and use a conjugate prior for them, which is awesome. Tau is in a different step, but it says bugs conjugate gamma. So conjugate, what does conjugate mean again? The distribution of the prior is equivalent to the distribution of, or it's the family of the distribution of the posterior. So when we specified a gamma prior for the precision parameter, which is like an inverse gamma for the variance, residual variance, then we can sample from a gamma prior for the, or gamma posterior for this parameter. And the way the algorithm is set up to work is effectively each iteration, you go here and you go here. So each iteration cycles between a step for the GLM and a step for the sigma squared, and every value has to have a chance to change to go through an iteration. Now, every value is likely to change because the way this is set up, they're being drawn from their posterior distribution. It's conditional posterior. So that's going to start lecture 8, which is our version of algorithms. And to look at this, the first step in figuring this out, there's two main classes of algorithms that are out there in MCMC. There's actually probably tons of algorithms. No, there are tons of algorithms. I don't know the full compendium of them, but there's sort of these two broad groups, and I think we've talked about this before. There's Gibbs Sampling, which means effectively, Gibbs Sampling is one version of it. We're drawing from a distribution without rejection. We're basically saying, let me grab a brand new parameter and use it. Grab a brand new parameter and use it. Those are thought to be very highly efficient algorithms. The alternative is one where we have to go and propose a parameter, and sometimes we accept and sometimes we reject. That's one version of that is Metropolis-Hastings or the Metropolis algorithm, and each of those goes along. So the reason why conjugate priors are so popular are because to specify a conjugate prior, you have to go and do all the math ahead of time. But when you do, you have a form of a distribution you can draw directly from. So conjugate priors make things efficient. And this first part of the lecture 8 is to basically show you how we derive a posterior distribution. That's the main part of it. After that, we're going to dive into what Gibbs looks like quickly, and we're going to dive into what Metropolis looks like quickly to compare between the two. All right? Cool. So you know your linear model. Here's the notation right here. We're going to make this into matrices, basically saying that the matrix Y, which is all of our data, big long column vector, n by 1, is equal to the X matrix, which is a design matrix. If we have capital V variables, this matrix has one extra column, so V plus 1 that column represents is a column of ones for the intercept. Right? And then we have error, which is another column vector. So this design matrix is multiplied by a column vector of the regression coefficients, beta. Right? So we put all that together. We have error, which is this long column vector itself. And often in the linear model, we say error when we go and do error as a joint thing. When we look at all the error rather than just one person or one observation's error, that now is multivariate normal, right? And that multivariate normal distribution for error has some type of is said to have a mean of 0. So the average error is still 0. The variance or the covariance matrix of this is sigma squared error when notating as sigma squared error. But really, in our linear model, it can be simplified. There's one simple, we're going back to the not location scale model. Here we have one residual error term times an identity matrix. Right? So it's this thing. So if you take this assumption of multivariate normal, we could break this down and look at the traditional assumption of E with that for one observation being univariate normal, mean of 0, variance of sigma squared. That's what this is doing, sort of stacking this into multivariate normal. And why I'm doing this in multivariate normal is because I want to show you the likelihoods for this in multivariate normal land. And I also want you to start thinking, a lot of these multivariate normals show up everywhere in linear models and of course in Bayes if you're trying to build an estimator. So what do we want to do? How do we, to get to Gibbs, to do a Gibbs sampling, we need to go and derive what the posterior is. The posterior is a product of the data likelihood conditional and the parameters, right? And the prior. So we have to look at both of these together to figure out how to make this work. And then of course we need some magic. People who've studied math like live in magic to me, because I wouldn't even know where to begin with most of this, but this is where you can kind of look up. For me, I follow what everybody else has done for trends until I get to some place where it hasn't been done before and I try to map those on. So I'm not great with this. I find it to be a difficult process, but I'm going to show you sort of where this goes. Let's start with data, the likelihood function, because there's sort of an art to this. You build the likelihood function and you look at it and you say, okay, I think this part looks like this distribution. So if I put this prior with this distribution, I'll get a posterior. And this other part looks like this other distribution. So if I put this other prior to it, maybe I'll get this posterior to it, right? So it's sort of this odd dance of what's our likelihood look like, and then what can we pick for priors that might make it work. Most often in your life, you probably won't do this, but there may be cases where you're like, hey, I could derive a prior, a posterior for that. So the likelihood function is multivariate normal. So this is the multivariate normal right here. Looks fun, doesn't it? This is where class goes downhill quick. So I rearranged a few terms, right? Make this look a little bit better. Now this part of the likelihood function, remember the likelihood function is the likelihood of the data given x and our parameters. X is observed in this case, so it's not actually random for us. So you only see x in its contribution to the likelihood. You don't see a distribution for x, or we won't see it tacked on. So there are terms here that we can drop that don't involve beta or sigma squared. All right, those are what we're going to call normalizing constants, and we tend to in Bayes just want to get those out of the way because we work with the core of the likelihood. It's less math. And the one that we're talking about here is this 2 pi. 2 pi doesn't have beta, doesn't have sigma squared. It's a constant. So when we remove that, we're left with the core of the likelihood function here, and that's where this little alpha looking thing, I don't know, what do you want to call that? Proportional to sign shows up, meaning it's not equal. The likelihood function is not equal to what's on the right-hand side, but this is the core that's driving it. And it's equal to this up to some type of multiplication by a constant or division by a constant, right? So now for the prior distribution, so that's our likelihood function. It's interesting to look at this because we can kind of see that this takes the shape of a normal distribution. Certainly multivariate normal, right? Because we kind of came from that. but it's going to be harder to say, okay, what do I put with this to make it work? The other part with it is, if you're really familiar with distributions, which I'm at one point maybe, but you know, I don't live there every day. For me, I'll go to my Rolodex of Rolodex. I go to Wikipedia. And I look at distributions and I see something that sort of looks like this form. And I got a sigma squared here. Oh wait, okay, so that shows up that, oh yeah, inverse gamma starts to take a form like this too, where we have a value raised to a power. Okay, maybe we can start to look at that. So that's where, like, breadcrumbs of where we might go with this start. So when we look at the priors for this, the part that's important to think is the prior distribution can be specified really as a joint distribution. The prior of beta and sigma squared together. Now, we often don't do that. A joint distribution prior, what does that mean? That means we could go and specify a prior that has a covariance between some of those parameters. We don't typically do that. We typically break this into the conditional distribution of beta, which actually is a joint distribution across beta, conditional on sigma squared, right? So we could specify covariances amongst the betas. But then that's conditional on a marginal distribution for sigma squared. Right, so we've got sigma squared. And why we do this is it allows us to sort of disentangle parts of these two distributions into more workable forms. The distribution of sigma squared we can just deal with by itself. The distribution of beta, that takes, well, it's conditional on a value of sigma squared. So technically speaking, we have to give it a value of sigma squared. That just means we carry sigma squared with us through it. It's not part of the normalizing constant. So here's some math that I would have never thought of to make this work. But I should have, sort of the learning process. We could rewrite, if we thought about how we might look at things, take a look at our likelihood function where this part shows up. Y minus x beta transpose times y minus x beta. We could go and form, we could actually show that this term on the left-hand side is equal to the term on the right, y minus x beta hat transpose minus y minus, times y minus x beta hat plus beta minus beta hat transpose times x transpose x times beta minus beta hat. That's a big step, but this shows up a lot in linear models. You're like, well, what's beta hat? Why this shows up a lot in linear models is we can substitute beta hat for a function of nothing to do with the parameters. It's only the observed values. X transpose x inverse, x transpose y. Right? And so what we end up getting from this, we take this term right here and plug it right up in there, where beta hat is, we get x times this. This actually carries a name with it in mixed models. It's called the hat matrix. We've heard that before. That shows up. But now if we do that, we can start putting this into a form where if we said, hey, I think I could rewrite my likelihood in a similar manner, where I can go and put these two together. So I go back to my likelihood function, and I'm like, hey, likelihood function, let's work with you a little bit and push you into a form where it might be one like this here. Actually, this is, pardon me, this is likelihood. It's not likelihood, this is the prior. This is the prior distribution. We go and say, hey, we're going to say that, I didn't put this, but what we tend to say is, for conjugate prior, once we start to see this form, we want to say inverse gamma is the prior for sigma squared, multivariate normal is the prior for beta given sigma squared. We can build those two products together into this form right here. When we do that, we can see that this part up here on the front, we kind of move terms around. There's this normalizing constant. Move terms around, drop a few constants, and we end up getting the prior for sigma squared. I'm doing hand waving because the honestly, this is hard for me to do mathematically, but some of you maybe will do it better than me. Probably most of you. When we get to, so once we have that conditional on, we can show that this other part that remains in this product of the prior, this part that's highlighted here turns out to be multivariate normal. So if we have this whole mess right here as a prior, By the way, in homework, this just becomes 1 over sigma squared. That's your prior, right? That's the part that goes away, okay? Hope that works. But we want to multiply this mess by the likelihood function up here. So when we do that, we can go and start to form the posterior. And so I'm looking up my notes for this class to try to figure out a nice way to show this. I'm looking at multiple sources. And I finally found one that said, hey, there's this interesting thing. There's this way that you can take a look at multivariate normal distribution and you can rephrase it. Like if z is the random variable and m is its mean and v is its variance, you can rephrase it to look like this form here. Because there's a lot of products and stuff that we can expand. Well, it turns out, when we do that, we just need our posterior for beta to start to look like that. We can get our posterior to look like that. We can say, hey, it's multivariate normal, the end, and sample from it. So here's sort of an outline of the derivation of it. This is our prior for beta, and it's multivariate normal. It's given sigma squared. What's in here is sigma squared 0 is not anything with the data. That's the prior covariance matrix for your betas. Right, so your betas, what does that mean? Okay, each beta that we did in our example before, we did univariate-wise. We had a mean and a variance. But if we put them all together, they're multivariate normal. The variance would be the diagonal of this matrix. Right? And in our example before, we had each beta as a univariate normal. That'd be like saying that sigma squared 0 matrix has zeros all in the off diagonal. Right? Beta 0 would be our mean vector for the normal distribution. So that would be like piling all those, when I put the mean at 0 the last time, just a big vector of zeros if we don't know where it is. We specified very uninformative priors before. So that's our prior. Here's our data likelihood itself. And when we multiply the two together, we can get rid of anything that doesn't involve beta, right? So there's a bunch of stuff that shows up that doesn't. Actually, we can get rid of both of those that it doesn't involve beta ahead of time. Really, what we're working with is this term right here and this term right here. Oops, no, the exponent part itself. And so we can note this part right here, the part that involves beta, can be expanded by matrix product. And we can do a similar thing for the data as well. Right, so we expand these matrix products. And so since these are in the exponent, when we take the prior and we multiply the exponent of the prior by the exponent of the data, when exponents multiply, they add together in the term that's in the exponent adds together. Right, so we bring those together and we end up having some stuff we can cancel. And first of all, we can get rid of some stuff because they don't involve beta. Move that stuff away. Other stuff we can cancel. And we end up getting a form, when we combine like terms, that fits this pattern right here. Right? So when we see that, we can say this term in the pattern above was the variance, the covariance matrix. Right? And this term in the pattern above was the mean. So we can use that to our advantage with these two values. And actually, pardon me, this term right here. So what it ends up being when we end up doing the variance inverse times beta n right here. So when we put that all together, the mean vector turns out to be this. This is the mean of beta in the posterior for the multivariate normal. This, pardon me, which can be written down here. We can move things over to make this work. So what does that mean for us? We have a variance, right? Inverse variance times the mean. Basically, this term determines the variance. This term is this whole thing is the mean. Now, all this together, that means conditional on a value of sigma squared, we can go in any step of the chain and we know what sigma squared 0 is, or the sigma matrix 0. This is our inverse original covariance matrix. We have x, we know that. We know our prior mean vector for the betas. We know our prior, and we know this term as well. So at every step of the chain, we know that beta is multivariate normal. Here's the mean vector. The variance times the mean is this. Actually, the inverse variance is this term right here. So that means we can draw a value from a multivariate normal with a given mean vector and a given covariance matrix at each step in the chain. That's what we're going to do in just a moment. How about sigma squared? We can do the same thing. Here's our likelihood when we rearrange terms. And we drop the terms that don't are constants or otherwise don't matter. Actually, this is the product of likelihood times prior right here. The prior is on the left, likelihood's on the right. We end up getting, by moving terms around, otherwise dropping them, we end up getting this form. And this is where your knowledge of PDFs work well. You're like, what is that? I've seen that before somewhere. It's inverse gamma. That's what that happens to be. I don't have that written for you here because I don't think in those terms. I don't. I gotta go. This took a lot of thought to go through, and even then it's not all that clear. But when it's inverse gamma, you can show that the two parameters of gamma happen to be, when we express this is what we call the effective degrees of freedom. It's effective sample size, or what our degrees of freedom error was before, plus n, that's this part. And we can show the beta vector is what we thought that effective sample size times the original value of sigma squared. This is our hypothesized value of sigma squared 0 should be. Remember, we talked about that last week. We said, what's a good value for that? And yeah, who knows, right? But then what you're doing with this is you're augmenting the original value with what's this term up here?
That's the squared residual.
That's right. Sum of squared residuals, right? Because you end up getting this y minus x beta. Y is a column vector, x beta is predicted value. So this is the column vector of all the predicted values. The difference between data and predicted value, when we do this product, then you end up getting a sum across the square values. So, sum of squares error. So what this is telling us about posterior is for variance, we're updating effectively what our value of sample size was by what n is, but we're also updating effectively what our version of variance is by some new value based on data. This is Bayesian update. The same thing would, if you were to look at the mean vector up here, it's the same type of scenario. The mean vector in the typical least squares version of linear models is x transpose x inverse x transpose y, but we've updated that with our values of belief about each of the terms that go along with it. Right, so it's an update. Now, here's the part that I always laugh at. Assuming, you always read this. Do you read this in stat? Let's assume the variance is known. Oh yeah, I know the variance. It's like, I like, oh yeah, that sounds implausible, right? If I knew sigma squared, I wouldn't be here teaching, right? I'd also know the lottery numbers that are coming out for Powerball, and let's just be real, there's snow on the ground. I'd be somewhere nice and warm. In fact, I'd have so much money that if I knew a storm was coming, I'd fly to some other place that was warm and go there, right? Just all the places I would be. But it sounds implausible, but here what we're talking about when it comes to Bayes, it's less assuming it's known. What we're going to end up thinking is, let's call this conditional on values of a chain, right? So when we go and sample beta in a chain, we're going to assume sigma squared is known. Well, we don't know it, we're just going to plug in the value of that iteration of sigma squared in the chain. And likewise, what beta is, flipping it around. How are we doing? Okay, thoughts or questions? Okay, so Gibbs sampling works in that way. And I have two files. One is Gibbs sampling, right here. So I'm going to clear my repos. This is under lecture 8. I have an R file that's called Gibbs Sampling. I also put the data file for this example of this. We're going to use the same data we used the last time. I tried to code the Gibbs sampler for our algorithm, but unlike JAGS, instead of using tau, the precision, I use sigma squared. So take that, JAGS. Because I don't think in precision. But okay. So we can load all our packages that we need. I can set our working directory, read in our data, and we're going to just quickly show this is the least squares estimate, the OLS estimates for the linear model we had before. Okay. Now in Gibbs sampling, to make this work, we again have to specify the number of iterations, number of chains, the burn-in, all that stuff. But we're also going to go now specify a prior, and we specify prior means, right? So we're going to do Gibbs sampling. We have our conjugate priors. We know what it should be. We can sample from beta. We can sample from sigma squared. But we have to specify the prior. The prior mean we're going to allow to be 0 for beta, and we're going to have a big variance for beta here. And now, remember, I'm not JAGS world. I'm doing variances, not taus. But this is actually the values of priors I did before. So what I do here, those are just the values. I'm going to load up a vector of means because we have 6 betas and a covariance matrix as well here. So this is, uh-oh, what did I do? N beta not found. Didn't run this line. So basically I'm saying all of my betas follow a multivariate normal. There's the mean vector of my betas. Here's the covariance matrix of my prior mean vector, prior covariance matrix, which means I know nothing about beta, right? Pretty much nothing about beta. Now, you'll note in the formula that I had before, there was an inverse sigma squared 0 that was there. So I'm just going to compute that once instead of doing that every step of the chain because it's a constant effectively once we plug in the values that we know. Now, this inverse function, I'm doing the not necessarily numerically stable version of it just because I want to show teaching-wise what's there. If I were actually going to code this in algorithm, I may choose a different way of figuring out what the inverse would be algorithmically. So just note that. We don't want to deal with, do we want to do with forward eliminate? What is it? Anyway, never mind. I can even say it now. Back substitution or forward substitution. Never mind. There are better ways. This what basically happens when you, I'll just say this right now, and I'm blanking on the words for it, but basically when you compute an inverse of a matrix in a computer, the inverse carries additional computations that don't need to be there because you can actually go take a form of the matrix that is triangular, either through a QR decomposition or Cholesky, and then using the triangular matrix, you can do a forward or back substitution in terms of a solution of a linear program, or essentially a linear, I'm blanking on it now, anyway. Haven't thought about this in a while. But that will save you steps in computation, and every step that you do, because that forward or back substitution starts with the triangular part of the matrix, and there's only one calculation, and you carry that forward, or you start to the bottom, you carry that backwards. That saves you calculation steps, so that actually means it's more stable numerically to do it different ways. But this is what we're going to do because I'm just don't want to go there. I can hardly describe it. But similarly, we're going to set the prior for sigma squared error. We're going to set the original sigma squared error to be just the observed variance, the unbiased version of the variance in our sample, and our prior number of degrees of freedom to 1. This is that uninformed prior I was trying to pitch the last time. Any questions on this so far?
Very quickly. Here you don't worry about the metrics being invertible because it's just a diagonal.
That's right, it's not a big deal.
In fact, here the inverse is very easy.
Yeah.
But if you allow covariances, do you take that into, in practice, you need to take that into account to be sure that it's invertible, or you don't worry about that?
Yeah, you would want to make that invertible. If it's not invertible, you'd have a problem. Now, I haven't gone through, there may be a solution to that we can use a generalized covariant matrix to do so. I haven't looked that up. But when it comes to the prior, in practice, to have a non-invertible, you know, a singular matrix there for prior, I don't see it happen. I don't see it. It's sort of like we can control that part of it.
And I think all the derivations still work if you replace the inverse with the generalized inverse.
Yeah.
Not positive.
Yeah, and it's
Sure.
a form of it, right? There's a number of generalized inverses, if I'm not mistaken, right? We typically think with the more Penrose.
The generalized
or whatever.
inverse of a symmetric matrix is not necessarily unique.
Right. Yeah. So you'll know. Yeah, that's it. So we'll have that. I guess that type of case could come up if you think of. There's another way of coding it. So in the linear model, there's lots of ways of coding it. We could have coded like SAS does when you do a linear model in SAS. They put all group. They basically make your X transpose X matrix non-invertible, right? Because if you dummy code your variables, they put all three. In our case, all three groups variables in, they're equal to the intercept. And they use that generalized inverse to come out with that. So you would have that similar issue you'd have to do, but I think you're right, the math works. I thought about programming it this way, and I thought, you know what, I'm just gonna keep it where I can hopefully describe it. So, how are we doing? So far, so good, just loading up priors here. So we're gonna convert those to alpha and beta. I'm renaming all of our stuff to y, x, and n, our y vector, our x vector, and n. And remember, this is that trick with the model matrix from R. I just went and grabbed the x matrix out of the model term. So I can just create that. There's my x matrix. And now here's the fun part. I need something to save my chains. I have a progress bar. And I create the total iterations. This, so now the loop for the syntax happens. I have a loop that goes, I'm running chains in serial. You don't have to do that. You program this a little bit more elegantly elsewhere. But basically, I'm going to start with chain 1, run chain 1 to its completion. Then I'm going to start all over at chain 2, run chain 2 to its completion, and so forth. And so to do that, I hope I set my seed, random number seed. Of course I didn't. I didn't set my random number seed, but that's okay. Anyway, here what you'll end up seeing is I have something to save my chain values that has all the parameters I have in it. And I randomly sample starting values up here for my parameters. And then I'm actually randomly sampling these from their prior distributions as well. But then I go through in each iteration. This is where Gibbs really works. So each iteration. Here, let's start this out, shall we? Let's imagine we're in chain 1. Here's our chain. What is our initial value of beta? Here are our initial values of beta. Wow, those are crazy. All right, knowing what beta should be, those are way off the charts, right? But watch the magic of what's going to happen, right? Sigma squared residual variance is 3907. Also kind of crazy, right? Let's keep going. So in iteration 1, we have to go and sample the beta vector, right? We have to go sample it from a multivariate normal. So we need the mean and the covariance matrix. So using those formula I showed you last time, I can create the covariance matrix of beta, right? That's that term right there. Again, this would be a little bit more stable in other ways, but it involves our inverse covariance matrix of our prior plus 1 over sigma times x transpose x. All right, so this term right here, this one, this is our the value of our the value of the covariance matrix at this step in the chain that we're going to use to sample our betas from. Okay? What's the mean vector? The mean vector, actually this term is the covariance matrix, right, from above, but I just put it there again. We use that formula, and we see the mean vector now looks like that. That mean vector looks a lot more appropriate. Why that's the case is because the driving force in sampling the mean vector comes from that x transpose x the term inverse. This beta inverse covariance is not adding a lot to x transpose x. You think of ridge regression, you're adding something down the diagonal of the matrix. That's what this is sort of doing, right? About that. Matrix product times x transpose y. And so it's sort of forcing us, this is the efficiency of Gibbs. We didn't have to go and jump around and eventually get down to where these values showed up. Gibbs said, oh, I pretty much know where the mean is. I'm just going to augment the mean. Here you go, here's your values. So there's our beta mean. So now we have to draw, so that's mean and covariance matrix. Those are the terms of that multivariate distribution, multivariate normal of beta. We need to go draw values of the multivariate normal. So we use the random multivariate normal. I transpose the values as come out because the way I'm storing the objects are a little bit different than how they come out of the value. And this is our current update of beta. That is our guess for the first iteration of what beta happens to be. Now remember where beta was before. Right? We had like 40,000 or whatever from like the initial value. We're way closer to where beta needs to be. Right? What's next? Let's do sigma squared. We again calculate the parameters of the posterior distribution based on the formula from before. And we use an inverse gamma and just draw sigma squared from it. And now sigma squared is 283. Getting much more in line with where we had saw it before. And the reason for that is because sigma squared is anchored by where your residuals were. So you think of this algorithm, in this step, we're anchored by kind of where our least squares estimate of the regression line is. So this gets us really corrected to where beta should be, within, you know, error, of course, it's based on the data that we have. And then this line says, oh, what are your, so if you're close to where beta should be, relatively speaking, your residual variances are going to be very close to where they need, or your residuals should be very close. So that goes and corrects sigma squared. Right, so all of a sudden, the burn-in part of our chain is gone. We're effectively burned in now. And this is why I'm saying, like, well, why did I pick the number of iterations to be what it is? Well, if I know I'm using a Gibbs sampling algorithm, when we see, I'm going to switch this for sigma squared in just a moment, it's not nearly as quick to get there. Let's go through the next iteration, right? So here, pardon me, one last thing. We've done this. Any questions first? Any questions? We sample beta, sigma squared. Iteration 1 is done. We save our values. We move on. So that's what we're doing here. I'm just grabbing those values and saving them in our chain. When we go back up, this is iteration 2. So if I were just to change this to 2, we grab a new beta covariance matrix from our posterior. You'll note the sigma squared in here is now based on the sigma squared we just drew from before. And here is our set of betas, covariance matrix. You'll also note the beta mean. Again, now it's different from the beta mean before, right, because that involves where our sigma squared happens to be. And now with that, we can go and sample a new beta. And here are our new betas. There we go. In the ballpark of where they were before, but sampling around. That's what we want to do. We want it to sort of sample this posterior distribution. Same thing with alpha, and we can go form our parameters for our inverse gamma for sigma squared, sample another sigma squared, and ta-da, we have another iteration done. No problem. Gibbs is amazing. That whole math part that I stumbled over is hard. But you get over that and you're like, wow, this thing really works. So let's just run the whole thing, shall we? I'm going to start all over. I created a progress bar to sort of tell us where we're at with chains. 1 chain, 2 chains. So it goes slower than JAGS because it's not hardwired. It's just R, base R syntax. And I'm doing loops. So we ran our 4 chains, close the progress bar. I'm going to go and make our posterior into an MC-MC object that's a coda deal so we can quickly look at output diagnostics. But let's take a look at this posterior. Oh, that's right, I'm in base R. Here's a plot of our posterior values. This includes all the values that we would have. There we go. It's a little bit easier to see. You'll note where we started, right? And then, right, there's like, if we were to think of this, this is all the chain, all the iterations of all 4 chains right on top of each other. And if we were to think about, okay, we need to cut off a burn-in period, this is what I said before, cut off, like, yeah, like the first iteration would be fine, right? Who does that? Yeah, I had a burn-in of 1. Drop the mic. But you could do that. I'm going to trim off a window. I trimmed off the first 5,000 iterations. I could do a similar plot. You can see now I don't have the first time. It's not spiked. But there's our posterior. And if I took a summary of a posterior, we could take a look at what the numbers happen to be here. Whoops. There you go. Posterior means and standard deviations. These are very similar to what we found with JAGs. Not exactly the same. Ballpark-ish. I may have done something wrong in code. There may just be an inefficiency because of the way I'm doing sampling with our least squares. There's more efficient ways of doing it. But there's numbers. Questions?
You set the seed, it will be the same anyway.
That's right. I didn't set the seeds, so. But even then, actually no. JAGs is using. I think JAGs is using R. No. I don't know where JAGs is called. So you can, when you code in a language that's not R, you can call R's random number generators. I think JAGs is doing that, so it may be the same. We may get the same values, but the order in which we're doing it may be different. And like they may grab sigma squared first, and yeah.
Anytime that you go with iteration, it's got to get exactly the same.
Yeah, we'd have to run a really long chain. So that's Gibbs. We like Gibbs, right? Questions? You want to see what it's like when it's not that efficient?
I mean, no. Let's just always hope it's that efficient, right?
Well, and that's where, like, my motivation for sticking conjugate priors where I can helps. But you'll note in our last example, the on-the-fly thing I ran in the first half of class, I didn't pull it up, but if I would have looked at the samplers for it, it would say Metropolis for the parameters in the variance. And so because of that, those were not necessarily as efficient. Right? Yeah.
Does Gibbs come in flavors?
There are different ways people talk about Gibbs. So there's combinations of Metropolis with Gibbs. There's something called Metropolis-Hastings within Gibbs, but Gibbs itself is typically drawing from a posterior distribution. What flavors are you thinking?
Such as in M+, there's something like P1x, P2x, P3, and random walk are choices you can make, and their documentation says nothing about what those mean. And so I didn't know if there were analogs that you would select from in other packages.
I don't know the answer. I don't know what those mean either. The way I look at it is, in some of the packages, like what we just did in the first half of class, it may have triggered some, it triggered Metropolis just for variances, but we're still doing Gibbs on the betas, I believe. I may be wrong about that too. Actually, no, I think those are. I think we can put a generalized covariance matrix in and do that. Not generalized, the full. So, long story short, those might stand for like a time where you're doing where everything can be Gibbs, or some could be, or none can be. I don't know exactly what they mean because I haven't used M+ that much for it. Haven't looked. I remember looking at the documentation once from you, I think, and going, this is why I don't use M+. Part of the reason. And this is on the internet. Anybody else want to complain about M+ since we're on the internet? You're anonymous. I'm not going to say your name, except for Lisa and Ariel.
I was going to say, for some of us, if you don't say the name, The accent, Terry.
Oh, right. Yeah, well, you know, anyway. But no, I think M plus is actually pretty good for a lot of things.
Well,
I just don't know what it's doing.
Yeah, like, so if you set up a model that's not possible, it will say, no, you need to change it to the other kind of Gibbs to do this.
Oh, okay, interesting. I had no idea.
So,
And so JAGS, if you set up a model like that, it goes and evaluates what you're doing and then switches or tries to align it accordingly. And so the trick with this, though, is sometimes you can accidentally trigger an inefficient algorithm in syntax in JAGS. Maybe that's like with, so I don't know about Git. M plus is sort of trying to make you understand it. In JAGS, in the syntax that you have for JAGS, there's ways. This comes up a little bit more when we get to measurement models and a little bit more when we get to logistic regression. But there's ways that you can, like we specify these intermediate variables here. Sometimes it can't tell what we're doing, depending on the type of model. When that happens, it might just make everything less efficient. Whereas if you shortcut it, if you don't like do this nice looking value of code, but you just literally take what I have highlighted there and drop it where you see weight hat, so you don't have the intermediate step, it might think otherwise about your syntax and go faster. I saw that with, and I don't know about JAGS as much. I haven't played as much with it. I've worked with a couple students who are doing that, and oh, look at that. We cut this out. Now sampler changes. Okay, we're making this work. The other part of it is the GLM package. If you can try to frame things to make it think it's a generalized linear model, which a lot of our psychometric models can be framed as, it also goes faster. If it doesn't know that that's it, or you don't load the GLM package, then it's going to sample each beta separately, which is a lot more inefficient, even if you're using Gibbs, because when you sample them together, that covariance matrix is helping us sample. And there's one step rather than steps that are conditional, which are sort of related. It eventually becomes like the covariance, but it's not as direct. So, that help? Anything else? Other questions? Should we look at Metropolis? Okay. So Metropolis, by the way, is where I learned MCMC. And I learned MCMC through like code. So this is how I grew up, like literally back in my day. You know, like the old man stories where, you know, I had to walk both ways to school, you know, with no shoes on, uphill in the snow, that both ways uphill, right? That was tough. This is it. It's like, oh. And I described Rod McDonald having a projector and underlining his handout slide, like literally when it was slides. Like if PowerPoint came first, would you call them slides?
you mean transparency.
Yes,
Right?
but we would call them the shortcut. I would call them slides because like they would slide all over the place if you didn't have a box for them, right? Or at least that's how they slide on the projector. I mean, I don't know. Just quick question, but I asked if Bayes or if this flexibility came first, would you learn ANOVA the same way? If PowerPoint came first, would you still call them slides? Presentation document, maybe? Anyway, so we're going to do this. To make things work for us, we're changing up. I'm going to go clear my environment again, and I'm changing up my what I'm going to do. I'm going to say basically that instead of having sigma squared follow that inverse gamma distribution, I'm going to take the log sigma squared and have that follow the log normal distribution. So now I've switched out of the conjugate prior for sigma squared. In fact, I switched to a prior that I don't know that I know for sure I can't derive what the posterior happens to be. Someone else may be able to derive it. It may be a form that we could do Gibbs with. It's not guaranteed. The conjugate prior is a direct way of doing it. The Jeffreys prior, by the way, you can use Gibbs sampling for. Jeffreys is not conjugate, but you can figure out the posterior. So the key to posterior, key to Gibbs is, can I go and derive what the posterior is, the complete, what we call the complete conditional distribution of the posterior? The answer is yes, Gibbs, right? Conjugate priors are such that you can always derive the complete posterior distribution, complete conditionals. So conjugate priors can always use Gibbs. but they're not the only ones that can. So, cool? So conjugate priors is not, if you have conjugate priors, you can use Gibbs. If you don't have conjugate priors, you may still be able to use Gibbs. That's where I'm going with this. It's not both directions. So we have it again. Now, in Metropolis-Hastings, the algorithm in JAGS has to do something called adaptation. So the way that Metropolis-Hastings works is that, let's see if I can make this work here. In Metropolis-Hastings, you may have a given parameter at a value. Let's say we have a parameter theta at a given value of a chain. Can you see this? Okay, it's my whiteboard. Right? So what you want to do, this is the theta, the current value of the chain. What you want to do is effectively say, well, I can't go and draw a new theta directly from a distribution. I have no idea what that posterior distribution should be, the conditional distribution for theta should be. Instead, I'm going to pick a proposal distribution. Right, so I'm going to go and come up with a distribution. So basically, I'm going to say, I'm going to draw a proposal theta. This is the proposal right there. And we're going to say, let's suggest, hey, chain, do you want to move to this theta? You may have that theta, but look over here. You want this one? Right? Sorry.
Let's make a deal. You want what's theta number?
That's right. You want what's behind door number 1, or do you want to stay with your own theta here, right? So this thing can come from any distribution, right? Any type of distribution that you want. That's the Hastings component of Metropolis-Hastings, right? So we could say, oh, I'm going to pick a normal distribution, right? Well, if we pick a normal distribution, when we draw, so this is for a potential value of what the new value should be, we could say, oh, let's take a normal distribution, let's just center it right at what the old value is. The mean of that normal distribution might be the old value. But the question with that is, what is the variance of that normal distribution, right? So you're going to say sigma squared what? Huh? I don't know. And that's where the tuning of the algorithm has to happen, right? So what happens in Metropolis-Hastings is the algorithm goes through, this is where JAGS is saying it's adapting the algorithm. Like when you submit it at first, or there's an adapt function in RJAGS that does this. What it does is it runs the Markov chain. It picks a value of sigma squared for you using some type of heuristic, right? We could think about this. All right, if theta here was one of our betas, right? We can pick a sigma squared that's somehow related to, let's say, what the least squares value of the variance of it should be, right? We know the posterior distribution for it should have that shape. But the reality of it is it doesn't really matter as much. It just matters about, you can eventually get to where you're going. It just takes a little bit more time. It's efficiency. So we pick a sigma squared. I don't know why I'm having this issue. Pick a sigma squared, run the chain, right? Right? We're not recording anything apart from the fact that we're seeing whether or not we are going and having, we're counting the number of times we accept the new value of theta star, right? Because if sigma squared is 2, why is it doing this? Anyway, if the variance of this is too narrow, right, then the values don't change very much, and it effectively may have a real easy time moving from one to the other, right? So it's inefficient, it's too narrow. If you're looking at the posterior distribution of what theta should be, it's going to take forever for you to get from one side of it to the other because it's too narrow, right? So if it accepts too often, forget it. We need a bigger sigma squared. Likewise, if it's too big, right? If you're here and you select something that's all the way over here, right? Your value is like 200,000 different. You'll never, it'll be so far away from where it needs to be for the posterior, you may never accept it. So we want to have this acceptance rate, which we're going to call somewhere where it's not too much, not too big, not too, it's like the Goldilocks, not too big, not too little, but just right. What is just right? Well,
42%.
47 and a half, thank you.
Excuse me, I just remembered.
No, well,
Arbitrary, exactly.
in SAS, I'm basing what I do here based on the SAS Proc MCMC. They said a paper from Andrew Gelman that said effectively something along those lines. I did not look up the original source. I'm citing SAS, so I don't know exactly what was said.
Very precise guesswork.
Yeah, exactly. Basically, we're trying to go and wiggle this around, but that's what's happening in adaptation. So basically, we need to pick what the algorithm needs to know when it starts is what's sigma squared for the proposal. If you're coding this to run JAGs, it's all kept from you. It's secret, or M+, or SAS. If you're coding this like I was, where I had to actually write the algorithm, you really got to worry about that, because if you don't pick that right, particularly in a linear model, or you don't let your chain adapt, you'll never get to, it'll take so long to get to the posterior, it's not worth doing anymore. Pretty much hand calculated, it seems like. So that's part of it. We're going to end up having, again, 4 chains. Each chain will be 1,000 total iterations. We'll chop off the first 500. But we're going to come up with something a little bit different to start this algorithm. We're going to have what we call tuning chains, or tuning phases. So before we start running an actual chain, we're going to run the algorithm. We're going to run a chain, but no, we're not going to keep the parameters we're interested in. We're just going to keep track of how many times we accept or reject.
Does the variance that's in it stay the same thing within a chain?
Yes. So within a, once you have adapted what you need to make the chain work for the official chain from burn-in through sampling, you have to have the same variance.
No, but what you're doing now.
What I'm doing now, for each tuning chain, which is like a phase, it's going to stay the same. I'm going to go and run up to 10 phases of 500 iterations. And each phase, what I'm going to do is I'm going to say, after 500 iterations, I'm going to see what proportion of times I accept versus reject. Based on that, at the end of that phase, I'm going to adjust the variance. And I'll show you the formula for it. It comes from SAS. I'm citing SAS on this. Until my proportion of times I accept is somewhere between 40 and 55%, or 0.4 and 0.55. That's sort of the window, right? So if I get lucky and I do adaptation twice, and all of a sudden I accepted 47% of my proposal values, we're just going to go into the new chain and do that. So it's the adapted, sort of adapting the algorithm. So the priors are going to be the same with the beta mean. Hey, I set the seed this time. And then sigma squared for our variance. We're not going to use tau. Let's see here. And actually, what I'm doing is for iterations we set. We're just going to try to do this. We're in chain number 1. So chain number 1, we again set up a placeholder to hold our data. We randomly sample our values of beta and sigma squared. And I'm going to set an initial proposal variance for sigma squared. So now what we're doing is Metropolis-Hastings for sigma squared. Once we have a sigma squared, we're going to go and do Gibbs on beta. I'm doing it this way because it'll still go pretty quick, because the Gibbs on beta gets us right where we want to be. So now I have to go and make this step to allow the tuning to happen. So while I'm still in this adaptation phase, this is what's going to happen. I need to calculate the proportion of acceptance versus rejected. I need to figure out if I need to change my variance. So this is the updating step. The actual value I change it to is a function of how many times I accepted versus how many times I wanted to accept. There's some theory behind it that I will skip in the interest of time. Here. So right there. So now what I've done is I know I'm in iteration 1 of the phase, the tuning phase. And again, I sample. Their beta works the same way. I'm sampling using Gibbs. For Metropolis-Hastings for sigma squared, though, it works a little bit differently. We have to form a probability. We have to form a probability that says we're going to accept or reject this proposed value. that probability comes from a ratio of values, right? I hesitate to go here because my iPad was not working the way I wanted. But what are those ratio of values? Basically, the probability of this ratio is equal to in this case, the likelihood of the data given the proposed value of our parameter times the prior value, of our proposed value of the parameter times the conditional distribution of what our previous parameter would be. So how likely would you have jumped from our proposed to our previous? Conditional, you were starting at our proposed value. That's the numerator. This part is data likelihood evaluated with our new parameter in it. This part is prior likelihood evaluated with our new parameter in it. And this part's a normal distribution where the mean is now our new parameter, and the other part is our, the other value is our old parameter. If it's symmetric, it will cancel. Technically speaking, to do this right, I actually sampled from, I think, a log normal distribution. So we may be symmetric, we may not be. If it's not symmetric, this needs to be there. The denominator of this is the likelihood of our data given our old value of the parameter times the prior likelihood of our old value of the parameter times the likelihood of jumping to our new parameter from our old value. That's the Metropolis-Hastings ratio. This thing forms a number that goes from 0 up, potentially up to infinity, right? But we're going to go and accept, theta star with probability r. So if this thing's above 1, we're going to guarantee we accept it. Right? So that's how it works. Interesting? The cool thing about this is, instead of in all that math we had to do previously, now we have a mechanism that only relates to, if you can write your model down, your model likelihood down, which is sort of the trick in Bayes, first trick, prior distribution and pick a proposal distribution, you can get estimates of a brand new model. You don't need to do the math if you wait long enough. Gibbs is faster, more efficient. You're going to see this change is going to be pretty efficient too. Right? Just take the practice of it. So in the code, I know we just have a few minutes left. I'm going to do this. Basically, I propose a brand new value of sigma squared. I'm drawing from a truncated normal distribution here. Right? So here's my proposed value. My current value of sigma squared is 7. My proposed value is 11. Truncated normal, I'm drawing from a truncated normal where the mean is the current value. The variance is my proposal variance. Remember, that is, it was 100 to start. It's 10, standard deviation is 10, square root of it. And it's truncated at 0, right? So we have the lower bound is 0, the upper bound is infinity, positive infinity. So it's half of the normal, effectively. So when we're really close to 0, this will be really not symmetric, and those Q ratios won't cancel. If it's a symmetric distribution, Q cancels. So now I calculate the likelihood of our result with our current value of the parameter. Right? So our current value, what's our likelihood of the data? Well, I need to plug in y, plug in the mean for y, which is x beta, and plug in our current sigma squared. If I take the denorm function, return a log, I get the log likelihood for each case, this thing right here. Oops. So there's a log likelihood for all of our observations. Take the sum over that, and I've got our model likelihood. That's like our deviance that we call deviance evaluated at our current value of the parameter. We do the same thing, but instead of sigma squared, we just change it to proposal sigma squared. All right. We do the prior. We have inverse gamma for both, but so for the current prior, we have sigma. For the proposed prior, we propose sigma squared. And now the Q factors, or the part of proposal given current, the value of proposal goes as x. The value of the mean is current. This is the denominator's value. And then current given proposal, is the x is sigma squared, the current value, and the mean is the proposed value. And so now I did everything on the log scale, but so instead of just converting it back to exponent and taking a ratio, I'm just going to go and keep the ratio on the log scale. It's the log ratio. So now I can, instead of multiplying these likelihoods, I just add them on the numerator, subtract the sum of the denominator ones. We're on the log scale again. So now that's our value of log r. That corresponds to a ratio that's bigger than 1, actually. All right, so what this is telling us is we're going to go and absolutely change from our current value of the parameter to the next value. And why I'm saying that is if we go and take the log of a random number, random uniform between 0 and 1, it's going to be negative. So we know it's going to switch. We do this, and what we're going to see is we accepted, and our new value is 11. And why we did that is because we're moving toward the middle of the posterior distribution. If we move toward the middle, we're going to accept. All right? So if we move away from the middle, there's a chance we accept, but a chance we don't. That's how this algorithm works. So you move away, yeah, maybe. Then all of a sudden, by chance, you draw another one that's toward the middle. Oh, yeah, I'm moving that way. Yeah, I'm going to move the middle. And I'm going to keep moving the middle. Okay, I'm going to propose one that's away. Oh, maybe. I'm going to keep moving the middle, right? So that's sort of what this is doing. It's trying to figure out where it is. Let's run the algorithm. The rest of it, let's just run it the whole way through, and I can show how it works. I'm sorry, we're pressed for time here. But it takes longer. This is the efficiency part, right? Those are the calculations in the first chain. Any questions while it's sampling? Some of them go quicker than others. You know why? The tuning will eject faster. So now, let's see if I can. This is the summary of what happened with our variances in each step, in each chain. These are our proposal variances. So our first chain, the first tuning phase, it was at 100, and we accepted 61% of the time. So it's a little too small, it got bigger. We accepted 60% of the time, a little too small, got bigger, we just barely made it. But we were between 40 and 55%, so we quit doing that. And then the same thing goes for step 2, at 100 to begin with, we jump to the right spot, but you can see where this is. Then, if we go and look at the plot, this is where you're going to see the efficiency issue really show up. Is that it can take, depending on where you start your value for sigma squared, it could take a long time to get where it goes, but it's still pretty efficient. This is these are all the chains. It's actually not bad when you zoom in here. But remember, I didn't record all the values of sigma squared in those tuning phases. And so the whole time we were getting pretty close with beta, because beta is doing Gibbs. Sigma squared is eventually getting to where it needs to be, so that when we finally start our chains, it's actually pretty good. If you start way off, or if you try to record the tuning, I should have shown that to you. So I'm pretty much out of time today. What do you think of Metropolis-Hastings? And that's it. I mean, yeah, that's it. If you love the math, some of you do. That's awesome. Do the math, make it work. Better be right. Make it work. But if you don't, hey, Metropolis works too. The cool thing about it, again, the cool thing is when I talk about so sometimes, most of the time, for a lot of the models, you might create JAGs or STAN or bugs are going to estimate them for you, and they'll figure out how to do it with Metropolis, right? But if you come up with a model where it may not work, you can still build this algorithm, right? You just have to figure out a little bit of code. It's not that complex. You're not doing derivatives. You're not doing anything else. The other part of this is, so that tuning and that adaptation that we're doing, we're trying to make it so that we have efficient proposals. The hybrid Monte Carlo, the Hamiltonian that comes out, is effectively trying to do the same thing. It's using, instead of using kind of this random walk approach where we draw inefficiently, it's trying to use a little bit more intelligent way of drawing what the next parameter happens to be. I won't get into it because we're not going to talk about JAGs too much in this. I'm sorry, Stan in this class, but you can find it in Stan as well. So it's probably, if you're going to build an algorithm, that one would be cool to use. It's more efficient than this Metropolis-Hastings, but it also involves math. It involves derivatives. So, ugh. Math is actually pretty good, but depends on what your tolerance is for it and where you go. Questions? Cool. One thing I'll remind you about, I have office hours on Mondays from 11 to 1. With homework being due this week, you're welcome to stop by. All right. All right. Have a great weekend. Thanks, everybody.